Good morning, everybody. So if you recall from your notes, we are looking at different reactions that help us prepare alcohols. Did anybody give some thought to the question I posed at the end of class yesterday? How would you like to see these reactions? I've made my decision, but I'm still open to hearing what you think. One of the reasons I wanted to pose that to you, to think about how you want to see reactions laid out, is to give you an idea of how you might set up a table of reactions if you build one. Do you want to see from each functional group what transformations can be done? Or do you want to focus by what type of alcohol can be made? Those are two different ways that you can set up. Even flashcards, you can set up what functional group am I making, or what functional group am I starting from. Sometimes they blend, but it's something to think about because it can help guide you as you're building a table. I've decided it's going to be most meaningful for us here to look at each type of functional group and the alcohols that they form. And then we're going to look at another way to prepare alcohols using acyl addition with our organometallic compounds. And there we'll focus on how do we make certain types of alcohols from organometallics rather than looking at what each functional group gives us. Okay, so sodium borohydride versus LAH. One of them is moderate, one of them is strong. Remember I pointed out yesterday that these reagents are essentially a source of H-. So we can say that the generic reaction is you take some carbonyl. This is not a mechanism that I often have you guys show. Not that it's a challenging mechanism, but there are a lot of other mechanisms that I think are more meaningful. And here's how I'm gonna write this out as not sodium borohydride and not a lithium aluminum hydride. I'm just gonna say generic metal. Boron's not a metal. Aluminum is, but this essentially generalizes it for us. Substitute that with boron, substitute that with aluminum. Hydrogen owns the electrons, which is why both reagents are called hydrides. So the electrons come with hydrogen and they attack the partial positive carbon, which breaks open that carbonyl bond.
Is this a mechanism that we have to know, or?
I will not have you show this mechanism, but I've heard students say in the past that seeing the mechanism helps them understand why the reagent is transforming it the way that it does. Now, according to the assumptions of bond line drawings, there is a hydrogen there. You're welcome to show it if you want to. You're welcome to show it, but this might be the most generic way because in a reaction, you're not always going to physically see that hydrogen. It's going to be assumed to be there. So keep it in your notes like this if you want to, or show that the hydrogen has been added. What change in hybridization occurs to the hydrogen, or excuse me, the carbon atom? How does the carbon atom's hybridization change? Goes from sp2 to sp3. This is considered reduction because hydrogens have been added to the carbon. The carbon has a lower oxidation state, a more negative oxidation state. We don't get that much into calculating oxidation states in our class, but you can say that bonds to more electronegative atoms make a more positive oxidation state. Bonds to less electronegative atoms make a more negative oxidation state. I have decreased bonds to oxygen, increased bonds to hydrogen. So reduction is sometimes shown as adding bonds to H or removing bonds to oxygen. Those are very similar. We're going to look at oxidation reactions in a bit as well, which are basically the opposite. It's increasing bonds to oxygen while removing bonds to hydrogen. That's generalized and not true in every case. Oxygen is not the only electronegative atom that changes the oxidation state of carbon, but it is very common. We know that this is being balanced by some other cation, either sodium cation or lithium cation. In the product here, we actually would just have a neutral aluminum or boron complex, but that boron or aluminum is still a Lewis acid, meaning it's welcome to accept electrons. For instance, like the electrons from the oxygen. Sometimes this reducing reagent can be used in several equivalences. So we're not going to focus on how many equivalences of reducing agent we have. We just say that we have as many as we need. I do want you to notice that some of these carbonyls will require more than one equivalence of H minus in the reduction. Several hydrogens will be added, not just one. But again, we're not looking too deep in the mechanisms here, so I want you to pay attention to the overarching functional group change. And if you're interested in digging into the mechanism, there are lots of resources for you there. Is that an alcohol? At the end of my little generic reaction, it's not an alcohol. And the issue with this not being an alcohol is I'm in strong nucleophilic conditions with that H minus group. So I don't want to have something that can protonate my alcohol present here. So these reactions are going to be followed by an aqueous workup, sometimes called an acid workup. You guys will see when I start doing reactions, what I'm going to demonstrate for you is first reduction, second aqueous workup. There are places that you will see sodium borohydride is given with methanol and without an aqueous workup. You won't see that on my written homeworks. You won't see that on the tests. You'll see the same thing for both reagents. But on active and on the internet, you're likely to find sodium borohydride written with methanol. I'll point that out in an example here in a second. Okay, that's our setup. Now we're going to dive into it. So I believe that we were under reaction 8, we were calling reductions. So maybe if you're making headers here, reduction of carbonyls, then first we're going to look at acid chlorides. Now, I'm going to give you guys specific molecules for our examples, but I do want you to feel comfortable expanding these functional groups onto other molecules as well. This compound is called ethanoyl chloride. 2-carbon chain. It can be reduced with sodium borohydride. It can also be reduced with LAH. Follow that up with an aqueous workup, an acid workup, H3O plus. H plus does the exact same thing here. You'll see that the 2-carbon chain is conserved. The bond to oxygen goes from a double bond to a single bond. How many hydrogens are added to the carbon in this reaction? There's 2 hydrogens added. So this is a 2-carbon or a 2-hydrogen addition, a 2-hydrogen reduction. I'm going to clarify a little bit. Acid chlorides, every time, form primary alcohols. There's maybe one acid chloride that deviates from this rule. One acid chloride that can be used to form methanol, and that would be systematic name is methanoyl chloride, but that's just a 1-carbon chain instead of having a 2-carbon chain. Any other acid chloride, regardless of what the rest of this R group looks like, will always be a terminal carbon, will always be a primary carbon. But here, and I'll show you guys how some other people show the sodium borohydride. They'll put sodium borohydride with methanol, and the product here is actually this 1 carbon gets reduced to CH3OH. So 99% of acid chlorides become primary alcohols. There's one type of acid chloride that could be used to make methanol instead. By the way, I don't think I mentioned this, but that table or that list that I have up there, we're going to see that list again later in the semester. We're going to add more carbonyls to it. That list is organized already by reactivity. Most reactive, oh, I told you this. Yeah, strongest partial positive on the left, weakest partial positive on the right. Aldehydes are also terminal functional groups. They end up on the end carbon. So aldehydes can be reduced to primary alcohols as well. Let's take benzaldehyde and let's reduce it with LAH followed by an aqueous workup. Does it have to be LAH? So this is the cumbersome part of putting these down in your notes. If you put NADH4, then you know that LAH can also work. If you put LAH, you aren't always positive whether NADH4 can do it as well. So feel free to always list NADH4, knowing that LAH can also be used. But if I ever put just LAH, it has to be LAH. That's for these 2 higher end groups. The product that we form here goes from being benzaldehyde to benzyl alcohol. Now here's something that I like to point out. The CO bond in the product is one of the CO bonds from the starting material. But it's oriented differently. We're drawing it in a different configuration. And that's really all just based on what is easiest to draw. I'm not used to drawing an alcohol where the bond goes up. It just looks a little bit more awkward. When you guys are doing synthesis, when you're doing mechanisms, it might be easiest for you to preserve the same bond line, all the same angles and stuff, to keep track of what bonds are where. How many hydrogens are added to the carbon in this reduction reaction? Two hydrogens are added to the carbon? one hydrogen. So we can fill in CH, CH2. One hydrogen has been added to the carbon. If it's not clear, I really encourage you guys to sketch them out so that you can see. And how did it get there? Just like this. One hydrogen left aluminum or boron, bonded to the carbon, broke open the carbonyl. There is, again, one case where an aldehyde can be reduced to methanol rather than a primary alcohol. And that would be this compound here, which is called formaldehyde. You guys have heard of formaldehyde before? We're going to talk more about nomenclature of these carbonyls in our next chapter, our next unit after the midterm. But form is actually a prefix that comes from the Greek for ant, because the Greeks harvested formic acid from ants, so they named the acid they got after the ant. But then that prefix form came to mean a one-carbon aldehyde group. So formaldehyde means one-carbon aldehyde with an aldehyde on the other side. Formic acid, one-carbon aldehyde with a carboxylic acid on the other side. There's also formamide. This would be formoyl chloride, kind of an awkward name in my opinion. I also want to show you another way that this is written. We can write this compound as CH2O. It actually is a little bit easier to write it as CH2O, but it's a lot less clear what is going on with the bonding. There's only one place those hydrogens can be bonded, that's to the carbon. And then there's only one way that the oxygen can be bonded, and that's a double bond to the carbon and oxygen. So formaldehyde, very small molecule, we'll use it in a lot of our syntheses to add just one carbon. And again, we can use first sodium borohydride or LAH, and we'll follow it up with an aqueous workup to give us methanol. How many hydrogens added to the carbon in this case? Still just one. So we're going to point this out, that the acid chloride, the carboxylic acid, and the ester, they all required 2 additions of H-, but the ketone and the aldehyde, they require just 1. Okay, I know I haven't, I kind of want to keep that up there, so I'm going to get rid of this generic reaction. Can you make a prediction about what substitution alcohols are formed by the reduction of a ketone? Will it be primary alcohols, methanols, or secondary alcohols or tertiary alcohols? Secondary alcohols, because that carbon of the ketone is already bonded to 2 other carbons. All right, let's take a compound we all know and love, acetone, and we'll reduce this with sodium borohydride or LAH. We'll follow it with an aqueous workup, and we'll get a compound that we all know and love. What is that product? Not propanol, not butanol. No, this one's ethanol. Ethanol, methanol, very common reagent in hand sanitizer. It is an alcohol. Good job. Oh, you guys are so close. Some people call it rubbing alcohol. Isopropyl alcohol or isopropanol. You guys see the isopropyl group, the 3-carbon group connected to the alcohol at the center carbon. That's what makes it isopropanol. Good. Again, how many ketones could you apply that to? As many as you want. If acetone looks too generic, spice it up. Let's put an aromatic ring on this side, and let's put an alkene on this side, and now we've got this much more complicated alcohol. It looks also a lot messier. But would you agree that that is still a secondary alcohol, regardless of what other groups I put around it? So, if acetone seems too much, make it a little bit more fun. From the reduction of carboxylic acids. And we're going to see carboxylic acids a lot in this semester, so I'm going to abbreviate this as Ca. We can get only one type, and that is primary alcohols. Unless, of course, we worked with formic acid, and we could reduce formic acid to methanol again. Now, I want to add something in here. No, I'll bring it back later. Never mind. Notice over the reaction arrows that I can only put LAH. This is not LAH or NABH4. How many hydrogens added to the carbonyl carbon? 2 hydrogens have been added, just like with our acid chloride. This is different from reducing our aldehyde and our ketone. I started with 2 oxygens connected to that carbon. In the product, there's only 1. Remember with the acid chloride as well, I had an oxygen and a chlorine, but the product had no chlorine in it. So this chlorine is leaving during the reduction, and one of these oxygens leaves during the reduction as well. So there's a byproduct in this reaction that has chlorine. There's a byproduct in this reaction that has oxygen. I just want you to pay attention to it. Your job is not to know the byproducts. I just don't want you to stumble at that.
So you can use an ABH for this one?
You cannot. Not strong enough. This is the first of our family that requires LAH. Esters. Now, esters are an interesting functional group because in reduction, because they will form 2 alcohols. One of those alcohols will always be a primary alcohol. The other alcohol depends. It depends on what the ester linkage is. This is a compound called tert-butyl propanoate. It has this tert-butyl group connected to the ester linkage. and then it's got a 3-carbon carbonyl chain. Tert-butyl propanoate. When this is reduced, which requires LAH followed by an aqueous workup, there are 2 alcohol products. One of them will always be a primary alcohol. The carbonyl will always be a primary alcohol. But I think that you can agree that if I had not put a tert-butyl group here, I could have put just a CH3. I could have put an ethyl group. I could have put anything. This ester linkage will form the variable alcohol. Do you guys understand what I'm trying to say by calling it variable alcohol? It depends on what the R group is. 2 products. One is 1-propanol. The other is tert-butyl alcohol. Any questions so far? Because we're about to get to the fun stuff. I want to do some practice with you guys. What happens when your compound contains more than one type of carbonyl? Well, it depends on what type of reagent you provide. So I'm going to show you guys the products from this one compound with 2 different reagents applied to it. First, we'll reduce with NaBH4, followed by an aqueous workup, and then we'll reduce with LAH, followed by an aqueous workup. Do you see the connection already about how multiple carbonyls with different reagents are going to react? I said earlier, we're not focusing on equivalences of reducing agent. The reducing agent will be whatever we want it to be. It'll be an excess, excuse me. But when I take this aldehyde and carboxylic acid compound, this would be called 4-oxobutanoic acid. And I reduce it with a moderate reducing agent, only the aldehyde is reduced to a primary alcohol. This gives me 4-hydroxybutanoic acid. Selective reduction. LAH. Well, that reduces both of these compounds, and I get 1,4-butanediol. Good stuff, right? Here's another fun one. This is a cyclic ester. Any biochemistry fans in here? Do you know what a cyclic ester is called in biochemistry? They call it a lactone. I don't know why. But it's basically a specific type of ester, a cyclic ester. In order to reduce this, of course, I need LAH followed by an aqueous workup. Can you predict the product that forms? Take this six-membered cyclic ester. First, look back on the board in your notes and see what is formed when esters are reduced. You're off to a good start then.
I was looking up what lactone was.
Was I right?
I couldn't read it.
You mean you couldn't read what your search said?
At the time.
Wait, I didn't do it with the.
No, I'm thinking more with the lactic acid with the ketone.
I was right, by the way, but that's okay. Lactose, I'm going to look up. Lactose is not a cyclic ester. Lactose is a sugar. I didn't know that. I guess it sounds like fructose and glucose and lactose. I thought it was a protein. Oh, wait, what is the protein that makes people lactose intolerant? Are people just intolerant to that sugar? Lactase. I think you might be right. I think, yeah, that's the enzyme that cleaves lactose. That might be what they don't have.
I've heard before I have that.
Lactic acid is strange. Actually, I'll use lactic acid as a practice for us.
Your body makes lactose when you're like a storage. And so it's like if you have a bunch of carbs or sugar, then it'll store it away.
But we know that we also ingest it through milk.
Yeah. So it's just not as broken down. But your body would probably break it down.
Your body would probably break it down and then store it again. That's interesting. All right, well, I'm going to come back to this one, but here is the compound lactic acid. It does have a chiral carbon, but we're not going to worry about its chirality. I want you guys to predict a starting material and a reagent based on what we've just learned with this reduction of carbonyls to synthesize lactic acid. You're right. I know. I'm going to come back to it. This is your next one. That's good. Oh, I think you've got too many carbons here.
Well, that was the one you wrote.
No, you didn't. You've got the right number. It does not form two products. One product.
Okay.
Yep. What does it always form? Two alcohols.
Okay.
It's always going to form two alcohols. One will be a primary. One might be primary, might be methyl, might be secondary, might be tertiary. Do you guys know there's no quaternary alcohols?
Is it stay cyclic or is it break?
It'll have to break. Yep.
Very good.
Good. Yeah. There we go. Yes. Very good. You're doing quite good. This one form, if you can see it, this is not really present here at all. But this works. Sorry, I didn't notice you had done that. This works. Now you've got to figure out what the starting material would be. Good. 1, 2, 3. 1,
Oh, yeah. I
You
edited that
mapped
out.
them. You started mapping them and everything. Okay. With the first one.
Susan, let me see if I can do it.
Yes. Good. So with this first one, mapping your carbons is a great idea. I'm going to number them in the ring. Doesn't really matter how I map, but I'm noticing that there are 5 carbons. I need to make sure that my product has 5 carbons. If you went back to this ester example and you said, how did I form those 2 groups? For instance, I could map these carbons as well. One of those groups gets carbons 1 through 3. One of those groups gets carbons 4 and 5. That means I'm basically cleaving my ester linkage. Carbon 3 becomes an alcohol. Carbon 4 becomes an alcohol. I'll do the same thing here. I'll cleave my ester linkage. Carbon 1 will become an alcohol. Carbon 5 will become an alcohol. So I'm going to have a 5-carbon chain, 1, 2, 3, 4, 5, with a primary alcohol on both sides. 1,5-pentane diol. Okay, so one of the reasons I wanted to show you the reduction of the lactone, when we looked at reducing the acid chloride, the aldehyde, the ketone, the carboxylic acid, they all formed one product, one alcohol. The ester forms 2 products, 2 alcohols. But that doesn't mean that they have to form 2 alcohols on 2 separate molecules. We still form 2 alcohols by reducing the ester, just so happened that they were on the same molecule. And then, of course, we had this practice where we had multiple carbonyls forming 2 alcohols. That's a bit different. Actually, this is an interesting way to look at it. We formed this 1,5-pentane diol by reduction of a cyclic ester. We could have formed this 1,4-butane diol also by reduction of a cyclic ester, but it would have been a 5-membered cyclic ester rather than a 6-membered cyclic ester. So we could have formed that a different way just based on what we're seeing here. What I saw from you guys here was, first and foremost, you recognized it would need selective reduction. I need to form an alcohol by reducing a ketone, but I am not allowed to reduce the carboxylic acid. So I'll use a moderate reducing agent, sodium borohydride. What type of alcohol do we have here? What is its substitution? That's a secondary alcohol. What functional group formed a secondary alcohol? Ketones. Esters can also form secondary alcohols. So there could be another way for us to solve this molecule as well. But ketone definitely makes the most sense. 2-oxopropanoic acid. Great. All right, let's do a few more. I'm going to do it the normal style. I'll put up one where you predict the product, one you predict the reagent, one you predict the starting material. apologize for everything being in orange. All of my other markers are dying. I promise next week will be better notes.
This one looks open.
You got it though. Yep. Just Mr. Oxygen here at the carbonyl. But otherwise, your carbon chains are perfect. Good job. And this one, you're right, it looks a little funky, but you did a good job of identifying which was the carbonyl and which was not. Sure. And this one, I think we agree, either would work, correct? This one always works. Mm-hmm. Good, you got your carbon chains right. That reagent works, so does the other. Mm-hmm. Yeah. Yeah, that's right. Because either one of them really works. This one is not quite right. You actually don't have any of the sorry, you have an ether in here because you have a carbonyl carbon, carbon oxygen carbon. So that's an ether, not an ester. What I would say is look at these two alcohols that form, and based on their substitutions, only one of them is allowed to be the carbonyl. The other one would have to be the linkage. I should have put more acid chlorides up there. I didn't have carboxylic acid in this either. So you agree both of them would work? Yeah, all right. Yeah. The carbon chains look good there. Good job. Okay. Yep. Yes. But make sure you got your numbers in there. Same here. Down below and up top. I do take points off for not having the steps. If you mixed LAH or NaBH4 with acid, they would just quench each other. They would not do what you want them to do. So if you don't have these numbers, you're saying, I'm mixing them together. And if you mix them together, they don't do their job. Yep. I try to come up with an analogy for it, but I have a hard time finding something you have to do first, then second. Oh, maybe landing a plane. First, let down the landing gear. Second, land the plane. You can't say, I will land the plane and let down the landing gear at some point during the same time. The landing gear might not be out all the way. I feel like that's not the best analogy. There's got to be something that's better. Still working on that last one? Did you get that last one? Yeah, it's funky looking, right? Yeah, good job. Now, how about you working on that last one still?
I was gonna start just have
Good. Yeah. You doing, Susan? Mm-hmm. That one was great. Carbon chains are all right. Both of our reducing agents went there. Oh, I already checked yours, right?
This is the ester.
Good.
So
And not just an ester.
I figured out the lactose thing.
Oh,
I
yeah.
was looking at my notes.
Nice.
So lactose gets broken down, turns into lactates, and then that goes into your liver because it's waste. And people who are lactose intolerant don't have lactase, or like don't have enough of it to break down lactate.
Ah, so their liver gets overaccumulated with lactate, and it poisons them basically. Gives them
It's harder build up. It's just because usually, like if it's lactose intolerant, your stomach just hurts a lot when you have dairy. So it's probably just the liver struggling to like get rid of the.
And lactate is actually just the conjugate base of lactic acid, right?
Mm-hmm.
It's that 3-carbon chain with an alpha hydroxy. It's just deprotonated. Interesting. So it goes from lactose, the sugar. It gets metabolized to lactic acid and then lactate.
You also create lactic acid in your blood.
Is that because you're metabolizing sugar and making energy?
Yeah, lactic acid is when there's not enough oxygen. It's like it's one. I don't remember exactly which part of the like citric acid cycle, but it's like there's not enough oxygen to reduce and or oxidize it. So then it just builds up.
It's a
The muscle
different, it's a different path, yeah.
Yeah, until you get.
I'd say not enough oxygen means you can't be oxidized. Yeah. I don't think you normally take oxygen as a reagent to reduce something else, typically oxidize something else. Okay, how are you guys feeling on the last one? Here's where we should start. Which of these might be allowed to be the carbonyl carbon, and which of them is not allowed to be the carbonyl carbon? If they're both allowed to be the carbonyl carbon, maybe we have 2 separate starting materials that could be reduced to the same product. But if they're not both allowed to be the starting material, the carbonyl carbon, then there's only one starting material. What did we say about esters?
If there were 2 carbonyls, would there be an aldehyde?
No, what I mean is there could be, like both of those carbons could be the carbonyl carbon,
Okay.
and then they get reduced. So you would have 2 possibilities of starting materials, 2 structural isomers that get reduced to the same product. I guess I could try to give you an example, which would be like, here's a 4-carbon chain and a 3-carbon chain. And this is going to produce a 4-carbon alcohol and a 3-carbon alcohol. But who's to say which of those primary carbons was the carbonyl? So I could have just as easily had that starting material to get the same 2 products. Does that make sense? Sometimes 2 different starting materials work. Can this carbon be the carbonyl carbon of an ester? We only saw one functional group from that family that forms a secondary alcohol, and that was the ketone. This cannot be the carbonyl carbon because there would be nowhere for the ester to link, nowhere for the OR group to be. Is this what we said is the substitution of the carbonyl carbon when we reduce an ester? We said an ester gets reduced and the carbonyl carbon becomes what type of alcohol? Primary. The carbonyl carbon becomes primary alcohol in the acid chloride, in the aldehyde, in the carboxylic acid, in the ester. Except in each of those cases where the carbonyl carbon could also form methyl alcohol. And that's what we have here is methyl alcohol. That's the only one that is capable of being the carbonyl carbon. Just one carbon connected to this variable alcohol. And then because it's such an awkward chain, there's a couple of different ways you might draw it. This would be probably my preferred way, but you can see the sec-butyl group, 4-carbon chain, butane, connected at this secondary carbon, and it makes sec-butyl alcohol. And what's on the other side of this? Just a hydrogen. If you want to show it, that's good. So that's a formate starting material. The one carbon aldehyde with another group. This would be sec-butyl formate. Form telling us this guy here. Most of you guys got this, which was the aromatic ring. Nothing happens to the alcohol on the right. I have a 2-carbon chain, or excuse me, a 1-carbon chain here to my first alcohol, and then a 2-carbon chain to my second alcohol here. That ester, cyclic ester, gets cleaved into 2 alcohols. I told you I did too many with esters. I should have put one that had an acid chloride up here. I should have done one with a carboxylic acid. Oops. How many correct ways are there to solve this last one? There's 2 correct ways. I could use NaBH4 because I have a ketone and an aldehyde. And if I can use NaBH4, I can also use LAH. Okay, why don't we take a quick break before we move into acyl addition. Let's just move around, get your blood flowing, and be back in here in 5 minutes.
It's lunchtime.
When you've been awake since 5 a.m., 9 a.m. is lunch, isn't it? When's dinner? 3 p.m.
Noon to 3,
Mm-hmm. No kidding.
but
Noon to 3.
I don't get to eat at that time.
Not today. You're gonna be in lab, watching stuff get protonated. Well, since nobody seems to want to get up and move around, I'm just going to keep going. We're on reaction 9 now, right? The 9th type of way to form an alcohol. This one we're going to call acyl addition. Do you guys remember what acyl means? Or what it infers? Yes, a carbonyl group, an acyl group. Kind of like when we did acylation with our aromatic rings. We added a carbonyl group. I do want to point something out. Addition reactions mean that you consume a degree of unsaturation. You consume typically a pi bond. What happens in reduction reactions? Pi bonds are consumed. What is being added across the pi bond is a hydrogen at the carbonyl carbon and a hydrogen at the oxygen. 2 different types of carbons though, two different types of hydrogens. A nucleophilic hydrogen from the reducing agent and an electrophilic hydrogen from the acid workup. I actually I meant to tell you guys, we can look at the mechanism if you guys are curious about how these cleaving things work. You won't be tested on it. So I'll only go over that if that's something you feel like is going to help you understand reactions better. So this is addition to an acyl group, but it's not called acyl addition. It's called reduction. Acyl addition is typically referred to when you have a nucleophile that's not hydrogen. And we're going to be more specific here. This isn't just any type of acyl addition. We're going to look at acyl addition with organometallics. Now I showed you guys from each of these different functional groups what type of alcohol I can make. What I'm going to do this time is show you what type of alcohol I can make, and then give you examples with the different functional groups. So first, let's look at methyl alcohol. CH3OH. Do you guys remember one of the characteristics of an organometallic reaction? I gave you guys some organometallic reactions yesterday, and I told you this is what happens every time you do an organometallic reaction. What forms?
Carbon-carbon bond?
Yes, carbon-carbon bonds form through organometallic reactions, or reactions with organometallics. Whether it is acyl addition or nucleophilic substitution, carbon bonds to carbon, nucleophilic carbon bonds to some sort of electrophilic carbon. What does methanol not have?
Carbon-carbon bonds?
It doesn't have a carbon-carbon bond. Methanol cannot be formed this way. We can form methanol by reducing formaldehyde, or reducing formic acid, or reducing a formate ester, or reducing a one carbon acid chloride. But methanol cannot be formed by acyl addition with organometallics because there is no carbon-carbon bond. Primary alcohols, you can use any organometallic that you want to use, but there is only one acyl group that can be taken through acyl addition to form a primary alcohol. I want to point out that the alcohol carbon is the carbonyl carbon. So the primary alcohol had to be a carbonyl carbon before. The primary alcohol means it's bonded to one carbon. That is the carbon-carbon bond formation from the organometallic. So beforehand, the carbonyl carbon was bonded to nothing. So primary alcohols with formaldehyde. And let's look at some examples. Here is formaldehyde reacting with methyl lithium followed by an aqueous workup. Remember, formaldehyde we can draw out. We can also abbreviate it. How many carbons will be in the final product? One carbon from formaldehyde, one carbon from methyl lithium. All right, I'm sorry. I do want to take a step back. I wanted to give you guys a generic form of the acyl addition, similar to how I gave a generic form of reduction. I want you guys to see what we're dealing with here. That's not acetone so much as it's a generic carbonyl. And that M just represents a metal. But in reality, that's either lithium or magnesium. Do you guys remember yesterday that we said cuprates don't run acyl addition? Cuprate runs conjugate addition. Cuprate is not a strong enough nucleophile to attack the carbonyl. So this M is really lithium or a magnesium halide. We can use Grignards, we can use organometallics, we cannot use cuprates. And if you were to show the arrow pushing, which I will not test you on the arrow pushing, that's why we haven't done a lot of mechanisms here. The carbon takes the electrons from the metal and attacks the partial positive electrophilic carbon of the carbonyl. Now, the carbonyl carbon is bonded to another carbon. Is that an alcohol? What do we need to follow this up with then? Yeah, we need to do some sort of aqueous workup. We need to do an acid workup to protonate the alcohol. That was like a big light bulb moment.
Today my brain's like a little bit behind.
Okay, one of the key things I want to point out here. The alcohol carbon comes from, this is a retrosynthesis arrow. It's a fat arrow, as I call it. And the fat arrow means, what did it come from? The alcohol carbon comes from the carbonyl carbon, is the carbonyl carbon. Where is the organometallic carbon? Bonded to the alcohol carbon. The alcohol carbon itself is the carbonyl carbon. So when we take a step back here and we look at formation of a primary alcohol with formaldehyde, here is my alcohol carbon. That carbon was the carbonyl before its carbon-carbon bond was formed. If I break that off, that leaves just one carbon in my carbonyl. And I don't want you to think that ethanol is the smallest it can be, so I want to give you guys another example. Let's take, I also want to show you that the reaction arrow setup doesn't need to be a specific way. I don't need to say, here's my carbonyl, I'll react organometallic, then an aqueous workup. We can actually say, here's my organometallic, I want to react the carbonyl, then an aqueous workup. So I'm going to take this ortho Grignard toluene, and I'm going to react it with formaldehyde followed by an aqueous workup. You see the similarities and you see the difference? I've just swapped what reagent went in front of the arrow and what reagent went on the arrow. But I'm actually saying the same thing. First, react organometallic and carbonyl. First, react organometallic and carbonyl. Second, have an aqueous workup.
Can you do the same thing for the other reactions?
you're not wrong that you could take any of these reducing agents and you could put them out front, and you could take any of these carbonyls and you could put them over the arrow. But it is a lot less common to show the reducing agent out front, and that's typically because you're starting with this, or you have synthesized this, and now you want to do something with it.
So in this case, it's because you could be synthesizing the.
Yes.
What is it? Toluene.
I could synthesize the organometallic and then introduce a carbonyl. We're going to learn how to synthesize carbonyls, and then I can add an organometallic. So you guys will do synthetic routes that approach this from either direction. Okay, here's my carbon that's a nucleophile on the ring. Here's the carbon that's being attacked. And it forms a primary alcohol. Orthomethyl alcohol.
We're gonna have one more. No. Okay.
You know what? Let's map our carbons just to be safe, shall we?
Okay.
And remember, I like to count through my nucleophilic attack. So I take a step back if I can, and then I attack. Here, I can't really. Methyl lithium attacks formaldehyde, and I get 1, 2. But here, I've got this carbon on the benzene ring that is attacking formaldehyde, and I get this 1, 2. Primary alcohols in both cases, would you agree? Both are primary alcohols in very different contexts. One is ethanol, one is benzenol. Let's form secondary alcohols. If my alcohol is connected to 2 carbons, how many carbons was the carbonyl carbon connected to before the organometallic attack? It's connected to 2 carbons. Take one away. That's your carbonyl carbon. It has 1 bond to another carbon. What functional group is a carbonyl with 1 bond to another carbon? Aldehydes. I'm abbreviating aldehyde here, CHO. Have I shown you guys this before? Common abbreviation for an aldehyde. It looks a little confusing, but I know the R and the H must be bonded to C. That leaves only one way to connect the O, and that's a double bond. Let's take a compound like inbutylene, and let's react it with benzaldehyde, followed by an aqueous workup. Okay, remember benzaldehyde is that aromatic ring with 1 carbonyl off of it, just the CHO. Now, I'm attacking it from this carbon. So I'm going to count through my nucleophilic attack. Carbon 4 attacks carbon 5, the aldehyde. So here's 6, 5, 4, 3, 2, 1, secondary alcohol. And I'm just going to map my positions again. 4 attacks 5. 5 is connected to 6. 5 is now a secondary alcohol. We're going to look at two different ways that we can synthesize a tertiary alcohol. One of them is with ketones, the other one is with acid chlorides. We're not going to spend a lot of time looking at the acid chlorides. We'll come back to it in a later chapter. Let's take 2-pentanone. Let's react it with vinyl Grignard. So Grignard connected right to an alkene. We'll follow it up with an aqueous workup. All right, I got to go in and check my carbons because I think I screwed up. I'm going to count through my nucleophilic attack. What's my nucleophile here? Oxygen is not the nucleophile. Oxygen is the nucleophile in the protonation step, but not in the acyl addition. What was my nucleophile here? I said I counted through the nucleophile, or through the nucleophilic attack. Hands off.
I'm like behind it.
It's okay, sorry. I know I go fast and I don't.
Organometallic, I guess. It's one of those things.
Yeah, our organometallic is the nucleophile. The organometallic is always donating electrons. So here I'm going to count through my nucleophilic attack. Carbon 2 attacks carbon 3. Carbon 3 is my carbonyl carbon. Now I'm just mapping. I'm not counting necessarily. So I'm going to say that carbon 3 is connected to a methyl group, and then I'm going to map the rest of these. I'm going to call these 4, 5, 6. So I should have 2 connected to 3, 3 connected to a methyl group, and 3 connected to 4, 5, 6 in my product. Here's position 1, 2, 2 attacks 3. 3 was my carbonyl carbon. 3 is now my alcohol carbon. That's good. 3 is connected to a methyl group. 4, 5, 6. Have I screwed up?
Yeah.
What did I do wrong? Too many carbons. Luckily, I mapped my numbers. I mapped my carbons. So now I'm not submitting this and losing some amount of points for having too many carbons. I can erase that carbon and make sure that I'm good to go. And maybe you want to draw it a little bit differently. I kind of drew it by just drawing a carbon chain the way I thought it would be. Maybe you want to start by repeating the carbonyls carbon chain and turning the carbonyl carbon into an alcohol, and then just doing whatever you need to do to connect the new group. But let's be honest, which of those is prettier to look at? Yeah. Doesn't mean that's wrong. You did it completely correct. It just, that looks more like an organic molecule. All right. Questions so far? Let's look at the formation of tertiary alcohols from acid chlorides. Now here's why we're not going to dive into this too much until our later section, I'm writing this as if it's one equivalence. But that acid chloride, like we saw even in the reduction, that acid chloride is not the same as an aldehyde and a ketone. That acid chloride is actually going to kick off its chlorine group after anything connects to it. So when one equivalence of this methyl group adds, the chlorine kicks off. That's a ketone. A second equivalence of this methyl group will attack the ketone that forms. So I'll end up adding 2 equivalences of CH3 to take that primary acid chloride and make a tertiary alcohol.
You don't have to like put that you're adding 2 equivalences of it. You just say it's excess and just have it flow.
Yeah, in fact, most people won't even say it's in excess. And here's the challenging part. You're not in the lab, but last week and this week in lab, they're doing a reaction very similar to this. They're taking a ketone, and they're adding phenyl grignard, so a benzene ring connected to MgBr, and they're attacking that ketone and making a tertiary alcohol. If you were to try to run that in lab, even with just one equivalence, you might not get a ketone. You're going to get a mixture of different products. So it's really hard to control the reactivity. Let's say you've got 100 molecules of the acid chloride, 100 molecules of the organometallic. 5 of those molecules react together, and now you have 95 molecules of acid chloride, 5 molecules of ketone, and still 95 molecules of organometallic. The organometallic is going to keep reacting with the acid chloride. It's also going to start reacting with the ketone, and it's going to do an addition reaction to the ketone that forms. So it's really hard to control just one equivalence only reacting with the acid chloride. So you might as well just do an excess amount, and to that point, most people won't clarify it. But we'll come back to that more later. Quaternary alcohols. How do you form that? What does, sorry.
You said you can't.
Can't. What does quaternary mean?
That's 4 carbons.
4 carbons connected to the carbon. Notice that a tertiary alcohol, I'm not describing how many carbons the oxygen is connected to. I'm describing how many carbons the carbon is connected to. Tertiary alcohol has a carbon with 3 bonds to carbon. How can I have a quaternary alcohol where the carbon is bonded to 4 carbons and an alcohol? Doesn't exist. It's not real. All right, and then this is not a reaction, but a word to the wise. Organometallics and carboxylic acids don't work well together. Carboxylic acids are acids. Organometallics are aggressive bases. The organometallic will not connect to the carbonyl carbon. The organometallic will just take the proton. All right, So let's do some synthesis problems so that we can start connecting these things together. By the way, there are multiple ways to do some of these syntheses. I want you guys to focus on reactions that involve acyl addition. As you look at them, are you brainstorming? You should be able to brainstorm pretty easily and say acyl addition. But what other things will you need to do? Sorry? No, I recognize what you're seeing. The example I gave for acid chlorides is the same molecule I'm using there.
Yeah, so that you will hear, but can I do this part or not? It has to be like this.
So you're actually mixing two things where you've got. Oh, I see. No, I would avoid putting an organometallic onto the carbonyl carbon.
Okay.
If you want to put an acyl group there, you could do just Friedel-Crafts acylation. And you might want to say, what type of alcohol do I have here? And maybe avoid the acid chloride because there's another way to make it.
Yeah.
What type of alcohol do I have here? What starting material could it have? Not to throw you guys off right in the middle of this, but I just realized the same idea we're going to come back to on Unit 5. It works actually for esters and acid chlorides. They do essentially the same thing. They both kick off a group, form a ketone, and can take on another equivalence. And in these reactions, in these syntheses, I would try to avoid that. Try to avoid the acid chlorides or the esters. There are easier ways to make these reactions run. Really close. Mm-hmm. Remember, in our generic reaction, though, this has to be followed by.
Oh,
Good. 1, 2. And thinking back to lab, you did this last week. You're doing this week. Isn't that kind of interesting?
yeah.
Freeman Crafts acylation. Not in this chapter, no. It was it was one of the first EAS reactions we learned in section 16. That's great. Good job. Yep. This does not. Oh, wait. No. So you're trying to do radical halogenation. This adds an anti-Markovan called HBr across the alkene. So it would take this alkene and it would make it 1 bromopropane. It wouldn't make it 3 propene. Yeah, it would consume the pi bond and it would add there. What you want is actually Br2 and light. And that does allylic halogenation. Yep. And that's great. Yeah, that's good. So I would say start by identifying the functional group, see where it falls. Is it primary alcohol, secondary alcohol, tertiary alcohol? And then try to work a step back. What could I have here? What could I have had here that could make this in just one step? And that might give you an idea of how to get to that. And then the same idea here. How can I take a step back? Yeah, good. We won't connect an organometallic to a carbonyl.
Okay.
Remember what carbon is the alcohol carbon? Yeah. In the step before it, the alcohol carbon comes from the carbonyl carbon.
Okay.
And the carbonyl carbon is the electrophile, the one that accepts electrons.
Okay.
Did that give you enough of an idea?
Yes.
Sam, do you want to put your solution up on the board?
For which one?
For, did I see both of them? Yeah, actually, both of them work great. So whichever one you want to do, just one of them is great. Thank you.
Isn't that tertiary?
It is.
alcohol?
Mm-hmm.
And so going back,
Yes.
you said don't do this one.
I would avoid it, which leaves you with that. Yep.
So a ketone has to be.
That's your ketone. That's the only one it could be. So what would need to be added here to turn this ketone into this? Don't get hung up on this
This,
reagent
okay.
being shown with this. This is just an example.
Okay.
Now you need to find the correct organometallic.
Oh, okay.
Is the Frigo whatever only works with the benzene?
Benzene and the acid chloride. So this is good, but it should be AlCO3.
Oh, sorry.
And methyl grignard is great. Is it methyl grignard or is it methyl bromide?
Magnesium.
Good. Good. That's perfect. That's what you want.
And then here I just saw that I'm sure this will go.
That's true, but I think you'll have a hard time getting from this to this. This is where mapping your carbons can be really useful. Do you see these carbons in the final product? Good. Then you want to make a way to get those carbons to bond the way they need to in that product.
Okay. Alright.
You're also missing one carbon off on this side.
Let me see.
Okay, good work, Sam. And I'm gonna try and walk you guys through the solutions quick. So there were two really good ways to solve the first one. Sam's shown us one of them, which is brominate the ring or chlorinate, and then turn the ring into an organometallic, organolithium or organomagnesium halide, a Grignard. Then attack a carbonyl carbon that is a ketone to make a tertiary alcohol. I made an organometallic. Here's the ketone I need. Here's the bond that Sam was looking at for me. Is that the only ketone that could have been used in the step prior? No. We could have taken this ketone. And we could have attacked that ketone with a methyl organometallic. And that gives us the final product. So how then do I get this ketone? If I'm starting with the aromatic ring, all I have to do is Friedel-Crafts acylation. Friedel-Crafts acylation gives me the ketone. Organometallic acyl addition gives me the alcohol. In the second one, if we're mapping our carbons, I see this 3-carbon group in the final product. I see that 3 bonds to 4. 4 is the alcohol carbon, which means in the step prior, 4 is the carbonyl carbon. This is the bond I'm going to try to make. So I need 3 to be an organometallic, organolithium, or a Grignard. And I need 4 to be an aldehyde. It's a secondary alcohol, which is formed by aldehydes. So here's my aldehyde, 4, 5, 6. So I'll do first my aldehyde, then H3O+. But the real question is, how do I get a lithium there? Well, in order to get a lithium there, I would need to have a halogen there first, and then synthesize the organometallic. That's not just any halogen, by the way. That's an allylic halogen. It's not vinyl, it's not connected to the alkene. It's allylic, connected adjacent to the alkene. And allylic halogens can be made by radical halogenation. Br2 and light gives me an allylic halogen. Lithium gives me an organohalide. And then acyl addition gives me my alcohol. I understand it's not necessarily an easy thing, but it is something that requires practice. The more you practice it, the more you struggle with it, the easier it's going to get. So I encourage you guys to go down to the old study materials, find the old homework problems, start applying them. Start looking at the written work that you have due at the end of next week. Start seeing if you can brainstorm what reactions will be in there. All right, I apologize for taking you guys over. Thank you for your time. Have a nice weekend, and I'll see you next week to wrap up alcohols, cover ethers and epoxides, and practice synthesis more.